Let's look now at visualizing the data that we obtain. So we're going to plot vectors and matrices, and from what we can visualize, we're able to draw conclusions about how the data relates to itself. So let's first just create a vector. A is linearly spaced from 0 to 2 pi using 1000 points. Note that the special reserved variable in Matlab pi that takes the value that we expect from maths. So the vector x is created in the workspace, and then let's simply take y as being the sine of x, and if we plot here x and y, then straight away we get the figure shown here. So this is a plot of y against x, and that's the sine wave graph. So let's look now at labeling those axes. Let's x label, and then we supply a string here. So a string is a collection of characters, and this function x label does require that there be a string as its argument. So a string, as I say, it's a collection of characters, it's not a number, and so that string is going to be used to create a label for us on the x-axis. So let's look at the figure. So here you can see that the x-axis is now labeled with this x, and similarly, as you might imagine, there's y label as well, so y label y. And in fact, let's just add more text to it here. We can say y equals sine of x, and you see it's printed that vertically on your y-axis. So that's how you can label your axes, and quite often it's the case that we'll plot more than one curve on the set here. Sorry, more than one curve on the set of axes. So we might need a legend for that as well. So we can write in here legend, and let's label that curve variable y. And you see we've created that legend on there. So that's your plot. You can also drop a grid on that plot if you want to extract or if you want to read off values. That makes it a little easier. So here you can see we've dropped a grid showing these particular values here. And that's your plot command. So that's the simple case where we're plotting a single curve against a given set of values here. And let's look at the case where we might have a second variable. So let's say z is equal to, well, let's take the square root of x, and let's plot that together with y. Now, our plot command, here it is. In the plot command, we've got x comma y, and then Matlab looks at this. It understands that these are two vectors of data, and if we add more arguments to that, it will detect that we now have a second set, x and z. And so inside this function, it will interpret this list of arguments as a request to plot y against x, as well as z against x on the same set of axes. So let's plot that. And you see here we've got y equals sine of x here, and y equals the square root of x over there. So in this case, we can imagine that we would need the legend command. It's more important in this case. So let's label those axes. That's x label and the y label. Y label y comma z, because those are the two variables we're plotting on the y-axis. So that's there. So that's what we have. Y and z are plotted here. The variable x is plotted there. And we now really do need that legend. So writing in here legend, and the first string is that y of x is equal to the sine of x, and the second curve is that z of x is equal to the square root of x. So this legend produces this box here with that text in it. Sometimes, well, the default position for that box will be there, and sometimes your curve will be in that region like this one is. So it's quite easy. You just click and drag that down. And there is a way to adjust that property, but we'll go into that later in this series of lectures. So we've got our two curves plotted here, and we've got legends for that, so we can distinguish between the two on the set of axes. But sometimes we would like to specify different line styles for these, and to do that it's quite easy. So let's call back the plot command. Here, where we're plotting y against x, we can in fact specify a line style. So let's insert the string here, and let's make that a double dash. And for the z, let's make that dash circle. So what this will do is, if we use a double dash there, that will draw for us a line with a dashed line. If in fact we used a single dash, that would just draw a solid line. So double dash for the dashed lines, and then dash circle will draw a solid line and use circles for the data points. Remember that x and y are discrete sets of points. So those are discrete points that this plot command is issuing. It is connecting those points, which can be problematic in that we don't always want to pretend that we've determined the values in between the values that we actually have. So in fact, in science, we shouldn't be plotting all those values in between, but you can suppress that. So if you wanted to plot the specific points, you could just use an X there, and it won't connect those points. So in fact, let's just plot it like that. And you can see here this line looks very thick now, and that's just because we used so many data points when we created the vector x. We used 1,000 points. So let's change that. Let's call up the statement for x. And by the way, I haven't shown you this trick before, but when you press the up and down arrows, you'll have to spider through all the statements that we've made in the workspace. So to speed that up, we can type the first few characters of the statement that we originally made, which was x equals something. And you see straight away it pulls up the x equals linspace command there. So now let's just use fewer points. Let's just use 10 points, 1e1 or 10. And let's recreate x, and similarly let's recreate y like this, and let's recreate z like that, and let's issue this plot command again. So you can see here now that the specific values for x and y that we actually do have data for is plotted here, and the vector for z is plotted over there. And in the case of z, we've specified to use this line style, so the places with actual data is represented with these circles. So that's how we can plot using line styles. And if we were to ask for the legend for these two plots, you can see here that it has in fact shown us it's labeled these curves, and it's showing us what symbols it's using to represent these. So this is extremely handy for us. You can imagine lots of instances where you might have to generate results like this and then create some kind of report, and you don't have the option to use color in that report. Then you can use line styles to distinguish between these sets of data. Alright, let's look now at plotting the results for a specific example. So this example is it's fairly chemical engineering in flavor. So that's the problem given here. We've got two components, A and B, and the molar masses are given here. You see I'm sticking strictly to SI units, kilograms and moles. So that's 20 times 10 to the minus 3. More conventionally, we'd show this as grams per mole. But anyway, we want to plot now a graph that shows how the mole fraction of A changes against the against the mass fraction of B. So we can easily show that the relationship between the mole fraction of A, so small xa, that's mole fraction of A, how that varies with the mass fraction of A in this mixture. And if you know your basic chemistry, we find that this is the relationship between a mass fraction and a mole fraction, right? We just use the molar mass to translate between the two. So we're going to write some code just to plot this. And it doesn't say here what range we should use, so let's just assume some range and create the code from there. So let's call up the editor. Let's just clear this old stuff. Edit. Okay. So let's run the usual initializers. Close all, clear all, CLC. And let's create first of all this vector x, small x. Or rather on the right hand side we've got big X, so that's the mass fraction. So big X is linspace 0, 0, 1, and let's use 30 data points. Right, and the molar masses are given to us, so let's just leave the data here. So the molar mass of component A in the question, we can see that's 20 times 10 to the minus 3, and so 20e minus 3 here. Not sure if you're familiar with this notation, but the e, when in between two numbers like that, means that the number in front must be multiplied by 10 raised to the power the number behind. So that's 20 times 10 to the minus 3 there. And MMB, the molar mass of component B is 40e minus 3, and we've defined already the mass fraction there. So we want to use the equation, so little x equals big X over the molar mass of A, and all of that is divided by big X over MMA plus 1 minus big X over MMB. So this is a little bit of an implicit step here. The mass fraction of component B in this mixture must be the same as 1 minus the mass fraction of component A. So that's there. So this is actually XB, and so that's why we divide there by the molar mass of B. Okay, so that's there. And now, why won't this work? Try to answer that question. Save it first. Let's video notes. So that's our set of simulations there. So here I'm just copying out the path, Control C to copy there, and just Alt-tabbing into the editor here. I'm just going to say let's save that in this folder, and let's name this EX01, exercise 1, and that will save it with an extension .m. So that's saved. So that's saved in this path here. But if we look in the command window, you see we're not in the right path there. So I did talk about this in the very first video, but we have to say here CD and the path name to change there, or you can just paste it in there. So anyway, we're in the right folder now. So let's look there. EX01 is available to us. And what we'd said was that this looks all fine. This looks like the equation we expect. But we are expecting some kind of error, and I hope by now you're able to tell me what that might be. Let's run it. Let's look.